All right, so here's my first attempt to do a video answer, and it's a tough question. It's from chapter 9, number 69. And this is one where you start with a chain that is hanging right above a table, and then you let it go. And so after a small moment in time, part of the chain has fallen, which they call X. And the other part then would be L minus X, meaning that the whole chain has a length L. And so that means at this point, a distance X is actually on the table. And so the question asks for what is the normal force pushing up from the table. And this is a tough one, mostly because it's going to take advantage or require you to think about the kind of the new description here of Newton's second law. Let me explain it this way. I'm going to take this table and divide it into two pieces. The first piece we'll call the normal force number 1 is what's supporting the part of the chain, which I'll just call M1, that is actually on the table. And the part that's still in the air, M2, is then making an impact. Link by link, it's making an impact here. And so I'll call that N2. And so the total normal force is the N2 plus the N1. And the N1 is probably the easier of the two. It doesn't involve anything new. So I'll start there. And maybe I'll just kind of circle the part of the chain that is already on the table, and I'll just do a free body diagram for that. And so what's pushing up is N1, and of course what is pushing down is M1G. And if we then write out the sum of the forces, and here's where I want to make a note. In the past, we've written this as MA, but what we learned here in this chapter is that would be the rate at which momentum is changing. And so we're going to take advantage of that because we're going to see that real important here on the impact, because these are the two forces that make up the total force. I'll call it the normal force. It's even, if I can say, the normal force. But it's then, in addition to that, the impact force, and that's the change in momentum. But I'm getting ahead of myself here because for this part of the chain, I would just say that's equal to 0. And so we would have normal force 1 pushing up, we would have gravity pushing down, that gives me a 0, and we just have the first normal force just equal to the amount of weight of the chain that's on the table. That's the part that hopefully is the easy part. Okay, here is then the hard part. And the hard part is where I will then draw a diagram again. Actually, maybe I'll get another page here. And so if I draw the part of the chain, which I have called M2, that is in the process of impacting here, I would write it this way, that the sum of all the forces equaling, and let me write this then as dp dt. Okay, so there's our new idea. And the forces then, and let me just put the gravitational force, M2G here, And so on this side of the equation, the forces would be the N2 pushing up and gravity pushing down. And here's where things become new. This would be the derivative of the momentum. Now, let me write momentum as its two pieces, mass times velocity. And then let me remind you of your calculus. Your calculus then says if you take a derivative of a product, we call this the product rule, then you would have the first times the derivative of the second plus the second times the derivative of the first. Now, here's where we need to interpret this, because right here, this is ma. This is the acceleration. This is that term over there. So in other words, this is m, and the acceleration is a negative g. And so combining it with the other side, n2 minus m2g, I can cancel that off. And this gives me the missing piece, or the new piece, and that is this second normal force. I like to call it the impact force, is the velocity times the rate at which the mass then is hitting. And so it's the speed at that moment, and then the rate at which it's hitting. So to answer this, we still need to do a lot of work, starting with then this one here, the velocity. And in that case, I'll just invoke the conservation of energy from last chapter, chapter 8. And what we see here is that how fast something is falling is equal to the square root of 2gh. And I guess in our case, if you come back over to this picture, actually I guess it's back here in this picture, when this link is hitting, this link has fallen down a distance of x. Maybe see it better here. And so this link here has fallen x. And in fact, every link has fallen x, although the x keeps getting bigger and bigger. And so I'm going to write this then as the square root of 2gx. All right. So putting that over to here, I would have the square root of 2gx for this part of the equation. And then I have this other part, the rate at which the mass is hitting. And here I'm going to take advantage of the idea of density. And the chain has probably a good approximation of an equal density, so I'll put density. And so that is equal to m per length. And so when I say density, I mean per length here. And I guess we could write this density in two different ways. You could say it is the whole mass of the chain divided by its whole length, or you can say it's a tiny piece of the chain over a tiny length of the chain, which I guess I will write as dx. And so if you rearrange this, saying a little bit of mass, you will have m over L times this dx. So now if we come down here, normal force number 2 would then equal the square root of 2gx. And now, in place of this dm up here, this dm, I'm going to put m over L dx. And then this dx over dt, this is the velocity, which, as we said earlier, was this up here. So this gives me another square root of 2gx. And so these two square roots give me 2gx, and then m over L. And so that's the harder one of the two. Let me keep going with a new page here. And so what I would call total then, which I said was N1 plus N2, now becomes, and we said earlier, come back here to the first page, N1 would just be M1G. And now the tricky part that we just did right here, the N2, that would be the 2GX M over L. And then we can also do a little trick here with M1, because we might say something like this. M1 is to the total mass. So this is the mass on the table compared to the whole mass of the chain, would be the same as the length on the table divided by this whole length. So M1 then can be written as M over L times X when we bring this over to here. And, and let me not forget the G. Okay, and then we've got the 2GX M over L. And I think these are like terms, right? They each have an M over L. They each have an X. They each have a G. And there's 2 here and 1 here. So it makes a total of 3 M X G over L. And that's the final equation. Yay!